Every monumental structure in modern history begins beneath the earth. Here in Minnesota, high-grade iron ore is extracted to build the backbone of America's most ambitious project. Heavy machinery operates continuously, scooping thousands of tons of mineral-rich rock daily. Only raw deposits with peak purity levels qualify for defense and structural applications, transported by rail straight to the FLUXIFY X primary processing depot. The raw ore enters the facility where advanced automation takes over the handling process. Mechanical separation begins immediately. High-frequency shaker screens and powerful magnetic rollers sort the material by grain size and density to eliminate unrefined slag. High-pressure water washing strips away exterior clay and residual impurities, leaving pristine mineral ore ready for high-temperature smelting in the main furnaces. Before entering the furnace, metallurgical technicians verify density metrics, ensuring every batch meets the exact chemical composition required for extreme structural strength. Inside the primary arc furnace, temperatures exceed 3,000 degrees Fahrenheit. The raw ore melts into a uniform liquid state, liquidating remaining structural flaws. The refined molten steel is carefully poured into heavy casting molds. Automated sensors regulate flow rates to prevent air pockets from forming within the cooling metal structure. Continuous rolling mills apply thousands of tons of hydraulic force, flattening white-hot ingots into ultra-dense structural plates built to withstand immense compression forces. As the plates cool under controlled steam beds, the steel's molecular grain structure stabilizes, finalizing the core strength of raw defense-grade metal. Before precision machining begins, shot blasting removes every trace of furnace scale, exposing pristine silver-gray alloy ready for high-tolerance milling. Computer-guided plasma torches slice through thick titanium steel plates, carving massive structural shapes within fractions of a millimeter. High-speed CNC milling cutters shape complex internal geometries, utilizing pressurized liquid coolant to prevent thermal distortion during heavy metal removal. 10,000 tons of hydraulic pressure form critical structural curves without compromising the internal integrity or grain density of the solid alloy. Components undergo specialized vacuum heat treatment, altering the molecular matrix to achieve maximum fatigue resistance under extreme stress. Rapid liquid quenching locks in surface hardness, giving the structural steel the durability required for decades of uninterrupted duty. Abrasive waterjets strip microburrs from bolt patterns, ensuring perfect contact surfaces when modules are locked together on site. Automated robotic welding systems fuse structural collars using continuous TIG passes, delivering airtight, load-bearing joins that exceed military standards. Precision grinding eliminates microstress risers along welded seams, ensuring smooth load distributions across all major structural nodes. Precision machined structural nodes are transferred to the subassembly floor, where individual elements begin taking shape as complete defense-grade assemblies. While automation handles heavy volume, master craftsmen oversee critical hand-finishing stages, applying decades of experience to micro-adjust every key surface. Manual verification ensures tolerances within microns. Every individual dimension is cross-checked against strict engineering blueprints before subcomponents move to final joining. Complex geometry requires human touch. Specialist welders lay down manual TIG beads along intricate angles where heavy automated arms cannot maneuver. Subcomponents are fitted together with meticulous care. Precision alignment pins ensure zero strain on load-bearing bolt patterns during structural coupling. Hydraulic torque wrenches apply exact foot-pounds of pressure to every structural fastener, locking the multi-ton assembly into a rigid single unit. Edge chamfers and stress points are hand-polished to remove microfractures, maximizing corrosion resistance and structural endurance under heavy fatigue. Critical dynamic joint faces undergo hand lapping with diamond abrasive compounds, producing fluid-tight metal-to-metal seals without needing soft gaskets. Every finished subassembly is hand-cleaned and prepped. Stripping fabrication residues prepares the bare alloy for advanced non-destructive testing. Human oversight remains the ultimate benchmark of quality. Decades of industrial mastery guarantee that every seam leaving the bench is built to last centuries, with all handcrafting operations finalized. The component enters the quality control wing for comprehensive non-destructive testing and verification. Inside the non-destructive testing lab, Components enter a controlled environment where multi-spectrum optical scanners map surface geometries down to single-micron tolerances. Ultrasonic transducers bounce high-frequency sound waves deep into the steel matrix, scanning internal weld structures for invisible subsurface voids or micro-cracks. High-energy industrial X-ray tomography penetrates solid titanium up to 12 inches thick, creating 3D volumetric renders that verify internal density from every angle. Magnetic particle inspections under ultraviolet illumination highlight even the smallest surface stress lines, guaranteeing flawless performance under extreme tensile loading. Sample coupons from every heat lot undergo destructive strain testing inside hydraulic load frames, proving tensile yield strengths exceed extreme engineering margins. Automated coordinate measuring machines verify three-dimensional geometry against original CAD models, confirming that every mounting face is perfectly true, once every non-destructive and dimensional test passes without exception. Formal engineering compliance documentation is signed and permanently archived in the final finishing booth. Components receive specialized multi-layer ceramic coatings engineered to withstand decades of salt exposure, weathering, and heat cycles. A high-precision laser engraves permanent trace identifiers into every finished unit, linking each component directly to its full metallurgical manufacturing history, fully certified, pristine, and verified beyond military standards. The structural components exit the quality wing to begin the final phase of their journey, to ensure these multi-ton precision components arrive on-site in flawless condition. Custom timber crates lined with impact-absorbing high-density foam are constructed for each module. Heavy-duty tension straps lock the component rigidly to the base. Rubber corner blocks prevent any surface abrasion during intermodal long-haul transport. Vapor corrosion inhibitor film fully envelops each crate, sealing out ambient humidity, salt spray, and atmospheric contaminants during maritime and overland transit. Final shipping manifests, center of gravity markers, and project tracking identifiers are applied to the exterior casing for rapid identification upon arrival. Heavy logistics vehicles maneuver the multi-ton packages through the main bay, beginning the transfer process from indoor manufacturing to outdoor transit haulers. Outdoors on the loading dock, multi-axle trailers designed for extreme capacity distribution receive the cargo under strict axle weight distribution guidelines, with all cargo secured and double inspected. Transport rigs prepare to depart the facility, joining convoy routes bound for major infrastructure assembly sites. From this single facility, completed components travel across the country, carrying uncompromising structural integrity to the heart of America's most critical projects. Installed at the core of human engineering triumphs, these components fulfill their ultimate purpose, providing absolute strength where failure is never an option. This is more than steel and titanium. It is the result of raw material, precision engineering, and human craftsmanship, forging America's future from origin to completion. Before full-scale integration, key structural nodes undergo extreme environmental validation. Thermal shock chambers freeze components down to sub-zero temperatures to test low-temperature ductility. Rapid induction heating follows instantly. Measuring expansion coefficients under extreme thermal cycles ensures joints remain dimensionally stable under intense operational friction. Dynamic hydraulic actuators subject structural arms to millions of accelerated fatigue cycles, simulating decades of continuous stress load in a matter of hours. Portable laser trackers record thousands of spatial data points, compiling a complete digital twin to verify absolute geometric alignment before subassembly tie-in. Once stress validated, subcomponents return to the heavy subassembly floor. Precision laser guides align interlocking collars with zero margin for mechanical interference. Cold squeeze hydraulic riveting creates permanent mechanical interlocks along structural seams, eliminating stress concentrations inherent to traditional threaded fasteners. Specialized elastomeric thermal barriers are applied over high-exposure sections, insulating structural metals against extreme acoustic vibration and localized thermal bursts. Secondary systems, including integrated lightning protection and electrical grounding circuits, are installed and tested to ensure total operational safety in the field. The integrated assemblies stand complete. Combining advanced metallurgy, robotic precision, and rigorous multi-stage testing, each module represents industrial engineering at its peak. As the staging bay doors open, These monumental structures move forward to their final destination, built to support America's most ambitious engineering feats. On-site deployment begins at first light. Specialized heavy-lift cranes anchor to reinforce staging pads, preparing to hoist the multi-ton structural modules into place. Calibrated rigging gear ensures load distribution remains perfectly balanced during the lift, protecting internal machining tolerances from torsional flex. Controlled by precision tag lines, the suspended assembly approaches its foundation platform, where high-strength anchor bolts await exact alignment. Field engineers guide primary mounting pins into alignment sleeves, matching factory CMM measurements with absolute precision on the installation grid. Hydraulic stud tensioners stretch foundation bolts to predetermined yield points, guaranteeing zero joint relaxation under heavy dynamic loads. Field welds tie the modular components into a monolithic load-bearing skeleton, matching the exact chemical and structural integrity of the factory seams. On-site quality control mirrors factory standards. Ultrasonic testing verifies that field-welded connections achieve full penetration without internal flaws. A final protective field coat seals exposed connection points, ensuring continuous corrosion resistance across every inch of the assembled structure. As night falls over the site, the completed framework stands as a testament to engineering excellence. Built to serve for generations to come, next-gen process, engineering the foundation of America's most critical projects. Precision from raw earth to final horizon. Integrated structural health monitoring begins during final field assembly. Embedded fiber optic arrays are routed internally to deliver continuous real-time strain telemetry. Precision fusion splicing seals sensor networks against weather intrusion, ensuring uninterrupted data flow from the structural core back to control centers. Laser alignment systems sweep across extended structural spans, verifying that full load-bearing assemblies maintain 0 mm deadweight deflection. Hydraulic jacking stations apply calculated pre-stress loads to auxiliary cable stays, balancing internal tension matrices across the entire engineering framework. Digital torque multipliers log exact fastening parameters into permanent digital records, verifying that every anchor meets structural specification. Aerodynamic composite covers are locked over exposed joint nodes, reducing wind drag forces and sheltering critical load sensors from direct weather exposure. On-site telemetry hubs process real-time structural data, confirming that physical load distribution perfectly matches predictive supercomputer modeling. Access ports receive heavy weather seals, protecting internal cable runs while allowing straightforward access for scheduled routine maintenance. A final physical walkthrough by senior field engineers confirms that every joint, sensor, and protective shield meets operational readiness standards. Erected with absolute precision, the completed structure stands ready, an enduring achievement of American industrial power. Built to withstand the test of time, final commissioning begins as primary power systems couple into the core network. Integrated subsystems energize, bringing active monitoring circuits online across the full framework. Thermal diagnostics verify full load continuity. Under simulated operational stress, joints demonstrate zero friction loss, confirming perfect stress transfer through every mated interface. With all live load tests verified and environmental systems active, field engineers grant final operational sign-off, concluding months of continuous manufacturing and field installation, illuminated against the night sky. The completed project stands fully operational, a monumental feat of heavy industrial manufacturing built to define a new era of engineering capability and perfected by FLUXIFY X process. Building the foundations of tomorrow today.